In this video, I am going to discuss about the application of Ampere circuital law. And already the first application of the Ampere circuital law means for finding the magnetic field due to a current carrying thin wire, straight wire. Already I have given in the previous video, and in this video I am going to give second means to find the magnetic field due to a solenoid by using the Ampere circuital law. Let a current carrying solenoid, suppose this one is a current carrying solenoid, and here I want to tell you two things here. Solenoid means, suppose if we will take a cylindrical base like this one here, and when a wire is bind over it, जब कोई वायर इसके ऊपर बाइंड कर दिया जाएगा तो उस वायर के दो एंड बचेंगे, and when the current flow through these two ends, then through each term the current will start to flow, and now whole the system is called a current carrying solenoid, and a current carrying solenoid is behaves like a magnet. So here, in case of a solenoid, let us consider a solenoid whose length is very long compared to its diameter. Let this one is a current carrying solenoid, and already I have told you a current carrying solenoid behaves like a magnet. So suppose this one is a solenoid, and experimentally it observed that in a solenoid the magnetic field inside the solenoid is stronger than the magnetic field outside. And here, if we look this diagram, in this diagram, this dotted line shows here at this point the current is going upward. जैसे कि ये कोई सिलेंडर है, इसमें जब हम कोई वायर टर्न करेंगे तो एक बार ये वायर ऐसे जाएगा, फिर ये ऐसे, in this way. तो current when going upward in this one, it goes like this. Downward at this point, it means the wire is bind like this one, and the current is coming at this end upward and here downward. So this one is the direction of the current swing. This one is not magnetic field. And due to this current carrying solenoid, these are the magnetic line of forces. And experimentally, it observed that these magnetic line of forces are straight and parallel inside the solenoid. And as we come near its end, then it goes near a little far. And inside this, these magnetic line of forces are straight and parallel. And this straight and parallel magnetic line of forces shows that the inside the solenoid magnetic field is uniform. ये magnetic line of forces है, और ये देखा गया कि ये magnetic line of forces इस solenoid के अंदर straight और parallel है, और ये straight और parallel magnetic line of forces ये बताती है कि इसके अंदर magnetic line field क्या है, uniform. And when we come near the end of the solenoid, then these magnetic line of forces will go far from each other, and when the magnetic line of forces goes far from each other, it means at these points the magnetic field is what we are decreasing. So inside the solenoid, magnetic field is stronger. As we go outside, the magnetic field due to this current carrying solenoid becomes weak or becomes very less. Let us consider the I naught is the current flowing through the solenoid. Suppose in the wire of this solenoid, what current is flowing? I naught. And since Ampere circuital law is applicable for a closed loop, so let us consider A, B, C, D is a rectangular loop where AB is along the axis of this solenoid, and this BC and DA both are very long. So this side CD is far from each other. Once again, you listen here. Let us consider. Remember this Ampere circuital law we always use for the closed path. And here I am going to apply the Ampere circuital law. So let us consider a closed path or closed rectangular loop A, B, C, D. And in this closed rectangular loop A, B, C, D, AB is along the axis of this loop. BC and DA both are long, very long, So side CD is far from this axis. It means side CD is far from the axis. So we can say here at point CD means for this length CD here magnetic field becomes very small. इसके कारण क्योंकि ये साइड CD बहुत दूर होगा जब इससे, तो इस साइड CD के पॉइंट के लिए इसके कारण जो मैग्नेटिक फील्ड स्ट्रेंथ होगी वो बहुत ही कम हो जाएगी या नेग्लिजिबल हो जाएगी. So let us apply the Ampere circuital law for closed loop A, B, C, D. Now we apply Ampere's circuital law to the rectangular path ABCD. As already I have told you, rectangular path means closed path, and you know Ampere's circuital law be applicable for a closed path. So now when we apply the Ampere's circuital law to the rectangular path ABCD, we can write whole integration B dot dl is equal to mu naught I. And remember this, here I be the current enclosed by this rectangle. Where I is the current, enclosed by the rectangle. And remember this, I is the current enclosed by this rectangle here, not the current in whole solenoid. What is the current in whole solenoid? I naught. But the current enclosed by this rectangle is how much here? Only I. So by Ampere's circuital law, whole integration B dot dl for this rectangle ABCD is equal to mu naught I. Now for rectangle ABCD, we have, since whole integration B dot dl you have applied for this rectangle ABCD. Now our aim is to find what is the value of whole integration B dot dl means for this closed loop ABCD, the value of B dot dl. We can find out whole integration B dot dl for this loop. How many length is here? First length AB, second length BC, third CD, and then DA. So whole this can be divided in four parts. A to B, B dot dl, because A to B, B dot dl means for this length, the value of B dot dl. Similarly, plus B to C, B dot dl, plus C to D, B dot dl, plus D to A, B dot dl. इसका मतलब होल लूप के लिए हमको B dot dl निकालना है, और पूरा लूप कितने वायर से मिलकर बना है? 4. तो हर वायर के लिए हम निकाले हैं B dot dl क्या होगा. But you see, this BC and DA, since BC and DA is not closer to the edge, it is near the axis of this one here, inside it here. So you can say BC and DA, the length of this BC and the magnetic field for BC and DA, the angle between magnetic line of forces with magnetic field and this length is 90 degrees. And in any vector, A dot B is equal to AB cos theta, and in theta 90 degrees, then cos 90 0. So whole this value A dot B becomes 0. So simply you can see here, this one B to C, B dot dl, B to C, B dot dl is equal to here D to A, B dot dl, B dot dl is equal to 0. Here I don't, because angle between vector B and dl is 90 degrees. And C to D vector B dot dl is equal to 0 here around, since CD is far from axis. CD is far from axis. So magnetic field. So magnetic field B becomes negligible. Now you look here. यहाँ पे दो चीजों का ध्यान रखिए. The value of B to C B dot dl and the value of D to A B dot dl. ये दोनों जीरो होगा. क्यों? क्योंकि B dot dl B dl cos थीटा और इसके लिए B और dl के बीच में एंगल कितना हो जाएगा? 90 डिग्री. इसके लिए B और dl के बीच में एंगल 90 डिग्री से लेते हैं. But C to D B dot dl becomes zero. क्यों? क्योंकि यहाँ B ही जीरो है, क्योंकि CD बहुत दूर है इससे. So at this point, the magnetic field distance becomes very less due to the solenoid, and when B becomes zero, then you can say this B dot dl becomes also zero. So now you see whole integration B dot dl for this rectangular loop when divided, then this quantity becomes zero. B to C B dot dl is zero. C to D B dot dl is also zero. D to A B dot dl is also zero. So what is left? Whole integration B dot dl is equal to A to B vector B dot vector dl. Now let, so whole integration B dot dl is only this quantity is left and rest all this becomes zero. So we will get A to B vector B dot dl, and A to B vector B dot dl, you see, for A to B magnetic field and this length both are in same direction. It means angle between vector B and dl becomes 0 degree. So A dot B B dot dl becomes B dl cos 0, and cos 0 is 1. So you can write here A to B B dl. And finally this is equal to, you can write, take B outside, A to B into dl. What is A into B to dl? A to B into dl means total length of AB. Total length of AB. And let the total length AB is equal to x. Let AB is equal to x. हमने मान लिया ये लेंथ AB जो है वो x के बराबर है. तो होल इंटीग्रेशन A to B dl ये पूरा क्वांटिटी किसके बराबर हो जाएगा? x के बराबर हो जाएगा. So A to B dl is equal to x, and now we can write this is equal to B into x. So finally we will get here the whole integration B dot dl or simply let's say a whole integration vector B dot dl or whole integration vector B dot dl is equal to B into x. So this is what here the value of whole integration for the closed path ABCD vector B dot dl is equal to B into x. Where x is what here? Length of this side AB. And now let us consider, let n be the number of turns per unit length. Now, let n be the number of turns per unit length of solenoid. मान लेते हैं इस solenoid के यूनिट लेंथ में कितने टर्न है? n. तो हाउ मेनी टर्न्स इन दिस साइड AB? तो इस साइड AB में कितने टर्न्स होंगे? हाउ मच हियर? Length of this is x. In unit length and turns. So in x length is how many turns? Nx length. Nx turns. It means in this one is Nx turns. And in each turn, what is current? I naught. So what is the current in this Nx turn? N x I naught. It means the current in this AB is how much? N x I naught, and the same current is enclosed by this rectangle. It means the current enclosed by this rectangle ABCD is how much here? N x I naught. It means I is equal to N x I naught. ये जो मैंने I लिखा था क्या था? Current enclosed by this rectangle. तो what is the current enclosed by this rectangle? पहले देखिए आप इस साइड AB में कितनी करंट आ रही है, वही करंट जो है इसमें सर्कुलेट करेगी. तो what is the current in this AB? How many turns in this AB? The length of this AB is x. In unit turns, how many? In unit length, how many turns? N. So in AB length, how many turns? Nx. In each turn of the solenoid, what is the current? I naught. So in this length AB, what is the current enclosed by it? Nx I naught. It means the current enclosed by this rectangle is how much here? Nx I naught, which is what here mu naught I. So simply you can say from this one is equation 2. From equation 1, whole integration d dot dl is equal to mu naught. At place of I we can write nx I naught. Nx I naught. And from this equation and equation number 2, this one is what here? Whole integration b dot dl. This one is also whole integration b dot dl. So now you can say mu naught nx I naught is equal to bx. So from these two equations we can say here, so mu naught nx I naught is equal to bx. Now x is cancelled by x, and now you can say b is equal to mu naught n I naught. This is the expression for the magnetic field due to the current carrying solenoid, long solenoid whose length is very large compared to its diameter. So here mu naught is what here? Permeability of the free space and number of turns per unit length. याद रखिएगा ये n क्या है? Number of turns per unit length of the solenoid, and I naught is what here? Current in that solenoid here. And remember this, we can write here n is equal to n by L, where n is the total number of turns and L is what here? Length of the solenoid. So if the total number of turns and length given separately, then how can we find the value of n? N by L. So in this way we can derive the expression for the magnetic field due to a long solenoid. And it observed that the magnetic field at the end of the long solenoid is half of the magnetic field at its center. And already have derived the magnetic field at the center. How much here? Mu naught and I naught. So what will be the magnetic field at the end of the solenoid? Half of the center. So you can say B at the end of the solenoid is equal to half mu naught and I naught. So in this way we can derive the expression for the magnetic field due to a long solenoid. And inside the solenoid, the magnetic field is straight and parallel. And already I have told you this straight and parallel magnetic line of forces indicates that inside the solenoid the magnetic fields are uniform. Now next application of Ampere's circuital law to find the magnetic field of a toroidal. And toroidal is also called a endless solenoid. So a toroidal is a hollow circular ring on which a large number of turns is formed. Means ये एक रिंग के साइज का hollow रिंग है जिसके ऊपर क्या करेंगे हम ढेर सारे टर्न्स को बनाते हैं. तो दिस वन इज कॉल्ड एंडलेस सोलिनॉइड क्योंकि इसमें हमको ये नहीं पता चलेगा कि इस सोलिनॉइड का एंड कहाँ है. And the magnetic field of a toroidal or endless solenoid can also be calculated by using the Ampere's circuital law. And when you will derive it here, then it observe that the magnetic field inside the core of a solenoid I am giving the direct, I am not going to give the derivation of it here. The magnetic field inside the core of the solenoid is given by B is equal to mu naught and I naught, where mu naught, as you know, the permeability of the free space, and is the number of turns per unit length, and I naught be the current carried by this endless solenoid. So remember this, toroidal is what here? Hollow ring on which the wire will be wound. And the magnetic field at the core of the solenoid is equal to mu naught and I naught. And remember this, in the case of a toroidal, or toroidal is also called endless solenoid, the magnetic field due to a toroidal is zero everywhere except at inside or within the core. Except within the core, the magnetic field due to a toroidal or endless solenoid is zero everywhere. Now, next topic is force on a moving charge in a uniform magnetic field. Listen, when a charged particle Q moving with velocity v in a uniform magnetic field B at an angle theta, then it experiences a magnetic force, or in short you can say then it experiences a force, and that force is given by F is equal to Q V cross B. Again listen here, force on a moving charge in a uniform magnetic field when a charged particle Q moving with velocity v in a uniform magnetic field B at an angle theta. इसका मतलब कोई चार्ज पार्टिकल Q जब v वेलोसिटी से किसी यूनिफॉर्म मैग्नेटिक फील्ड में एंटर करे एट एन एंगल थीटा, मतलब ये B है मैग्नेटिक फील्ड और ये थीटा डिग्री पे वो एंटर करा विद वेलोसिटी v, then that charged particle will experience a force, and that force is given by in the vector form F is equal to QV cross B. So since force is a vector quantity, so it has both magnitude as well as direction. And the magnitude of this force, magnitude F is equal to Q, V cross B is equal to VB sine theta. Like already have studied in the class 11, the cross product of two vector A cross vector B is equal to AB sine theta. In same way, V cross B is equal to VB sine theta. So Q is already, so we can write here QVB sine theta. This is the magnitude of that force which is experienced by that charged particle. And now what is the direction of this force? Actually, the direction of this force is perpendicular to the plane containing vector V and vector B. वेक्टर V और वेक्टर B से मिलके जो प्लेन बनेगा उस प्लेन के परपेंडिकुलर ये फोर्स काम करेगा. But here also we can find the direction of this force by using the some laws like Fleming left hand rule, or simply you can say right hand palm rule. Easiest method is what I am telling you, right hand palm rule. And remember this, already right hand palm rule I was given for finding the direction of magnetic field, and same right hand palm rule also we can apply for finding the direction of this force. So dear student, always remember this, when a charged particle Q moving with velocity v in a uniform magnetic field B at an angle theta, then it will experience a force whose magnitude is how much? QVB sine theta. So magnitude of that force you can calculate by this one. And how can we find the direction of this force? So for finding the direction of this force, look here. This one is the right hand palm rule I am going to use for finding the direction of this force. And when you will use this right hand palm rule for finding the direction of the force, then simply first, क्या याद रखना है? You stretch your this first forefinger together, and this one is the thumb. Thumb will always put, or this thumb is always pointed हमेशा ये थंब किसके डायरेक्शन में रहेगा? इन द मोशन ऑफ पॉजिटिव चार्ज पार्टिकल। कैसे पार्टिकल के जो चार्ज पॉजिटिव चार्ज होगा वो जिस डायरेक्शन में मूव करेगा उसी डायरेक्शन में थंब रहेगा। या तो कहिए मोशन ऑफ पॉजिटिव चार्ज या डायरेक्शन ऑफ करंट, दोनों चीज रहिए। मीन्स योर थंब विल बी पॉइंट आउट in the direction of positive charge or in the direction of current. All these first four finger will keep in the direction of magnetic field. इसको magnetic field के डायरेक्शन में रखेंगे, इसको मोशन ऑफ चार्ज पार्ट पॉजिटिव चार्ज पार्टिकल या डायरेक्शन ऑफ करंट, दोनों। तो ये पाम जिस डायरेक्शन में काम करेगा वही बताएगा डायरेक्शन ऑफ फोर्स। Once again, listen here, how can you find the direction of this force? This point should be very clear. For finding the direction of the force, you stretch your right hand. Even the many rule is given in your book, but I am not running behind all these rules. Better you make a clear concept by using a fixed rule, which is easy for you. And I think maybe this right hand palm rule is one of the easiest method. So remember this, for finding the direction of the force, magnetic field, I was given you move in the direction of current. तो आप ये बनाइए दिमाग में कि अगर हमको मैग्नेटिक फील्ड का डायरेक्शन निकालना होगा तो हम हमेशा करंट के डायरेक्शन में मूव करेंगे। अगर हमारा राइट हैंड पड़ेगा उस पॉइंट की तरफ, मैग्नेटिक फील्ड डाउनवर्ड, लेफ्ट हैंड पड़ेगा तो अपवर्ड। ये मैग्नेटिक फील्ड के लिए बना लीजिए। एंड फॉर फाइंडिंग द डायरेक्शन ऑफ द फोर्स, कोई भी फोर्स हो, अभी मैं यहां बता रहा हूं चार्ज पार्टिकल के लिए, आगे बताऊंगा कि जब करंट कैरिंग कंडक्टर मैग्नेटिक फील्ड में रखा जाएगा तो उसके ऊपर भी फोर्स लगेगा। तो देयर आल्सो वी यूज राइट हैंड पाम रूल फॉर फाइंडिंग द डायरेक्शन ऑफ फोर्स। तो यू मेक a clear concept for finding the direction of this force. Always we stretch our four finger like this one, right hand, four finger and this one. All these finger together will keep in the direction of magnetic field. ये चारों फिंगर एक साथ मैग्नेटिक फील्ड के डायरेक्शन में रहेंगी। ये थंब हमेशा रहेगा either direction of positive charge or direction of current. Then the direction of this palm will be give the direction of the force. Now here a case arises, if the charge is negative, then so there you will use left hand palm rule. लेकिन बच्चों याद रखना ये कोई रूल होता नहीं है, ये केवल एक बनाया गया है जुगाड़ मेथड से। राइट हैंड पाम रूल पॉजिटिव चार्ज के लिए, तो लेफ्ट हैंड पाम रूल नेगेटिव चार्ज के लिए। ये रखिएगा हमेशा डायरेक्शन ऑफ नेगेटिव चार्ज, डायरेक्शन ऑफ मैग्नेटिक फील्ड, then this will give the direction of force on that negative charge. So this is the easiest method for finding the direction of the force. Suppose one example I am giving you. Suppose this one magnetic field. And a charged particle plus q is moving with velocity v in this. So what is the angle between this v and b? V and b, how much? Here b is perpendicular to the plane of both directed inward, for you downward. तो magnetic field is inward like this. ये magnetic field है. And this one is velocity of this positive charge. Angle between them 90 degree. So how much force experienced by it? QVB sin 90. It means the force is QVB. Now the question is here, how can we find the direction of this force? To use the right hand palm. मैंने क्या बताया था, ये चारों फिंगर किसके डायरेक्शन में? मैग्नेटिक फील्ड। यहाँ मैग्नेटिक फील्ड किस डायरेक्शन में है? इनवर्ड, परपेंडिकुलर टू द प्लेन ऑफ बोथ डायरेक्टेड इनवर्ड। मैग्नेटिक फील्ड का डायरेक्शन ये। This one in the direction of motion of what charge? Positive charge. Positive charge plus q इस डायरेक्शन में चल रहा है तो इसको इस डायरेक्शन में कर दिया था। Magnetic field inward. So this palm is going upward. It means that positive charge will experience a force in this uniform magnetic field in what direction? Upward. But if this charge is negative, तब क्या होता? तो नेगेटिव के लिए इसको मत लगाइए, नेगेटिव के लिए आप इसको लगाइए। मैग्नेटिक फील्ड इनवर्ड, नेगेटिव चार्ज इधर इधर जाएगा, ये नीचे, इसका मतलब नेगेटिव चार्ज के लिए फोर्स किधर लगता है, नीचे की तरफ। So in this way, you can find out what the direction of the force experienced by a charged particle when it enter in a uniform magnetic field. So dear student, today you go through this topic here, what I have discussed here. In the next video, again I will give you some more topic regarding to uh, some more important points regarding to this topic here. Thank you.